Hello everyone. So let's get started. Can you guys hear me?
Yeah, I can hear you.
Great. Yeah. So today I'm going to tell you something interesting. Let me first get a good marker. Great. So I know that you guys have been playing with Jupyter Notebook, and maybe you can say that why did I not tell you before? There is a Google project by Google. So they made free Jupyter servers. So usually people set up Jupyter Hub. So that thing is called Colab, C-O-L-A-B. So I'm going to show you how to use it. So you can use Jupyter Notebook online. So let me see if I have, give me a second, yeah. So yeah, so that is a free environment for running Jupyter Notebooks. So let me go over to my computer and show you how to use it. So I'm just going to launch this meeting. Okay. So let me see again. Okay. So let me share my screen and okay, great. Great. Okay. So you go to Google and look for Colab. Colab Google. It's a Google project. So here you will see it's a collaboratory, and it's a Python data science handbook, and other stuff are there. So then you go to click on this link, and you can look for notebook, or you can open a notebook, and this is going to be saved onto your Google Drive. So you have to log in, and you can even use GPU. So there is also a tutorial how to get started with this. This way you do not need to install anything. So here you see it's directly stored on my Google account, and I can name it as first Colab. Okay. So, and I can say print hello, same manner. So I think the first time to start it, it takes some time. After that, it gets easier, faster. So say for I in range, I'm just going to print some numbers, 10, print I. So here you go. So you can practice also in Colab, and you can also monitor here how much RAM, disk you are using. This is my Google Drive. This is a RAM, and there are a lot of options. So this is to make it easier for people. And I think here, this is, the interface is slightly different. Like this is how you toggle between code and text. So I'll let you explore at home. If you do not want to install a Jupyter notebook, then you can use Colab. Any questions about this before we move on to our actual class? material? Okay. All right. So let's go back to where we were last time. So last time we were doing pandas. So before that, let me create a new notebook for today's class. And also we'll cover a little bit of last time's class. So let me stop sharing and I will open a new notebook first and go back to the last. Let me see where I should start with. Okay, great. So last time we were doing share screen. Okay. Yeah, this is where we were. So let's recap quickly. Last time, somebody was asking if I could create a data frame. This is how to drop a table. So I had a data frame from pandas and I want to drop it. Before dropping, you can choose what axis to use. This is to say that drop this row, okay? And then once you drop it, then we show that, oh, now it disappeared. So that was the idea. So let me see if I'm missing anything for you. Okay, great. So that is there, okay. Right. So then I have and if you do in place, then it drops it right there. Then it's in the same variable or data frame, it drops it. If you do not put in place, then you will get a new one where it will have that row missing. So if you don't want to do, if you want to do in place, you should do in place. This is a permanent change. So then what we were trying to do is that can we add automatically on the fly new columns? So we are creating column names and values. Of course, values will have to be of the same size as there are rows. And then here, this is a simple, I'm adding a new column with values. I can also automatically drop values. Then I could do some instead of this parenthesis where, you know, for example, column name, you can in fact put logical statements like this. Anything greater than 30 will get a false. Essentially what happens is that if you have an array or structure same size of true and false, the ones that are false will not be shown. So here it is showing all the ones for programming more than 30. So that's what it's showing. I'm able to control the rows. This is for controlling a row. So similarly, series, Delhi, so you know you can subset, but that is temporary. It is not a permanent change. It's just making query. But here again, it's in place true. Then I'm again printing it. Where else? So again, we were subsetting it. This time we were subsetting it because we permanently dropped it, and then there was nothing. So this query is made on this, and DFST has become permanently this. Okay. So then we showed a bunch of queries. Then I showed that what happens if you, instead of this dot or any particular column, equal to Delhi. So it checks every cell. And for every cell that is true, it will show the number if it is Delhi, otherwise it will not. So here is an idea. So here we are showing this query. And only the Delhi is shown, you see. All others are showed NaN. What else? So this is the true, this is the logical statement. I'm nesting it. All greater than 5 and also Delhi. So you can do nested. Any questions on that? Then I was showing that whatever you return from these logical statements, you do data type. It's essentially a data frame of logical, like this logical booleans, and it's just saying that all are of Boolean type. That's where we stopped last time. So is there anything else we want to add here? So let's see. So there let's see. So we have learned dropping columns. Okay. So here is another thing I wanted to show you. So suppose you want to know the value of some location. How do you access it in a data frame? So let's look at a data frame now. Let's go to our favorite one, DFST. Okay, DFST. Okay, so it's not defined. That means I have not run this notebook. It's been the same since last time. So what you do is you go, to the top here in this, and then you say that run the cells. It will run it from the top to the bottom. So it's running the cells. Okay. So what about this now? Is it going to work? No, it did not. Run all above, actually. Run all above. So this star means it's still running. It's going to run. So it's running through all the steps. So you'll see this. Yeah, it's getting run one by one, everything, the whole history. Right. So this, yeah, so something we set some columns, we wanted to add some columns and it didn't work. So let's figure out why it did not work. Okay, here, length of values doesn't match length of index. So that means here I was trying to fit something because I was changing the code in the middle. So here, accidentally, I am creating this new column and then I want to add 4 values, but there were 4, actually 5. Last time I was going back and forth. At one point we had 4. So let's make sure it's the same. Otherwise, your data frame wouldn't work. So that is there. We took care of it. Same thing. I have to change it here. Okay. So that is, oh, this is for A. That's for B. Yeah. Sure, I could drop it. And then now run again, run this. Let's keep going. Let's keep going. Okay, great. Now, okay, so now you might want to ask this question. This is great, but how do I actually get one row or one location? Let's see, DFST. So it supports a few functions, iloc and loc. That's what I'm going to talk about first. Let's talk about first loc. What does it mean? So it means location. So for example, if you want to use index B, okay, so there was pandas, what did it say? Okay, key error B, right? So sorry, the location. So the loc, yeah, so loc B. Okay, so location B, essentially what it does is that it tells you about the entire row. So that's what it's saying. So this is how you can access individual elements. So what about you want to access location and name? So in that case, you have to use two kind of indices. You have to do two indices. Let's see. Comma. Does it do that? Well, RITI, because so it is a comma that you have to make sure that does the indexing. So there are two ways of accessing this using the location function. Always the index name, and these are labels, right? Column names or labels. The index is before the comma, and the second is the name, is the column. So I combine them. So it's like a coordinate. This is 0, 0. But now there is a trick here. What is location? LOC. Is it a function? Any guesses? What is it? Is it a data structure? Let me see here. This is something to do with Python, and that you'll. I want to make sure that you know about it. So essentially, anytime you write a tuple, this is about tuple. When you write a comma 5 in Python, it's a tuple always. If you do explicitly, then also it's a tuple. So essentially, what you are sending is a tuple here, nothing else, except without the parentheses. Let's try here. So essentially, it's a dictionary sort of thing. It looks up for this tuple and tells you what it is. You see, it's the same thing. That is something to know when sometimes function replies or returns two values. Like you'll see statements like in Python, like a comma b equal to function, or whatever function name, some func name, whatever it is. Essentially, it's returning a tuple. Anything you see, and if you see tree, it's a tuple of tree. Any questions on this? Okay. So do that. Okay, great. Just want to make sure. Okay. So this is the idea of location. So now let's see what if I want to pick these two things, RITI and at 41 and city Delhi. How do I segment it? So let's start here. So let's remove these redundant parentheses. You can also put an array of them. Why just one column? You can also put. So it tells you about B and RITI. It's the same thing, except it's a full index. What if I add X? So you can, instead of one name, you can put an array. So you see now you are returned and in two rows, actually two names, 1 and 2. So let's see here. Also, I do an array. So okay. So long story short, you can actually subset it in different ways. Instead of with this comma, you can in fact put tuples of arrays of indices and columns, and they will return you those combinations. So first it will pick X and Y's, and from there it will select names. This is very helpful to subset data. So, does anyone have any guess what I should do to pick this? New York, Delhi, and these A's. Any guesses? So this should be C because it's New York. Oh, hi. Okay. Okay, guys.
Yeah, it should be city, age, C, and
Okay. Yes. So I apologize. My loudspeaker sound was low, and if you spoke, I did not hear that. But I could hear auditing.
Okay.
Yeah. I apologize. So yes,
Yeah.
city and X, and then here. Yeah, exactly. So this is how you can select a subset. But sometimes I may want to do some quick calculation, index thing. I may want to iterate through a whole data set. Is there anything I can do programming wise? Let's see. I want to show you something interesting. For loop, we know in Python is very useful. And in df, I'm trying out something. Is there anything I can, can I actually create a dictionary from city to age? Maybe it's just a dictionary that I want to create for whatever reason, right? So in that case, so what you could do is this. First, let's see what I get by doing this. Do I get anything? Okay, I get an array, right? So what about I get another array side by side? Let me store it in a variable to make things easier for you. So in X, I store something. So for A in X1, and you'll see something interesting here that I could print it like an array. Great. So what is the big deal, you might say? Well, A's I can put it in another array. Great. So I want to accomplish something. I want to line up the city and age side by side. How do I do that? This is not going to work. So what you use is something called a zip command. Zip zips two arrays of equal size as groups. So let's see what we get here. Maybe it will, you see, you get tuple. In fact, here the entire A comes as a tuple. What if I want it separately? I want to call it A, I don't know, C as in city, A as in age. Okay, so you can do that. And suppose I want to create a dictionary for some reason, DICT dictionary that has, city to age, say, city to age. So what did you do here? Here you do I have done. It doesn't print anything, but I'm just going to print what is in the dictionary here, just to examine. So we have created a dictionary. So that means from the table, you can come all the way to a dictionary for Python manipulation and programming. Any questions here so far? Okay. So if by any chance, if you feel that, I couldn't hear you, feel free to post the chat so then I can see the, I'm making sure that, I can see your questions. Okay, so I have shown here two ways of using how to use lock a location and index it by the index level, a level, and the column level, row or column. and we have shown even an array. So then it applies, selects the rows, and also then subselects on top of it the columns. Here is a guess. Another thing you can do. What if I did not put an? What if I did not put? I put an empty array. What do I get here? I got nothing. What if I do colon, range? This means everything, right? So I got all of them. So that is used to pick the entire rows. That's another thing to know. So that location, you index it by the index values. What about if you are only comfortable with exactly like first row, second line, these kind of things? So then I want to make sure that you can, another thing here, let's look at the same command here. If I do not put an array, first let's look at the type it is, what type it is. Type. This is a data frame. What about this? If I do not put an array, it is only going to pick one row. Then it became a series, you see, because only a series has one line. So why is it a series? That's because it is just one row of things. That's a series. And it has become, these are like a kind of index. So, okay. So there is another useful rule. What if you did not want to always index with XC row index names and column names? Can I do the same thing? Let's say I want to access again row, this first one. DF. Says 0. What would it mean? Okay, so I have to put, not directly here, I have to put ilog. So this is essentially indexed by an integer. So this gives you the entire row, but I want the first row, first column, that riti. So you get riti here. And I wanted to get, say, this subsection, city and is CNX index. So this should be 1 through 2, and then it would be here 0, 1, 2, and 3. So you use ilog, index, look, access by. So 1 and 2, and then I get 2 and 3, I think. That's what you get exactly. Or you could write like this: 1, 3, 1 more, 4, and then you remove that. Here, it's the same thing. So this is how you can index. Another one is that you can directly access the value, is called I@, another functionality. It's called I@. DF at say 300, say riti it will be. Oh, I@, oh, no, so this is not, this is, sorry, echo. Okay, so this is riti. So you can also use I@. So these are the different ways you can access. So then there are a few other functions, but that's not that important to us for now. We can come back to it later. But today I want to also, there are different conditional things and then multi-index, which we will come back later. But today I want to focus on another topic. So I want to create a new Jupyter notebook of June 8th.
Hi, Kishori.
Yeah.
I have one question.
Yeah, go ahead.
Yeah, what is the difference between this ILOC and IAT?
Difference between what? Sorry.
ILOC, ILOC, and IAT.
IAT exactly points to one location only. So, so ILOC, as you see, I'm going to back to it. I'm picking the whole range of things, several things together. Let me go to ILOC, yeah. So ILOC, I'm subsetting. But this ILOC, exactly specifying one coordinate, is the same as actually IAT. So IAT has to do with exactly one coordinate location. But you could achieve this with also ILOC one coordinate. But ILOC is more powerful in that sense. Another advantage in these kind of programming constructs is that sometimes then you might ask, why did they create IAT if ILOC does the job anyway? The question to usually these kind of things is that sometimes it's when you implement constructs like ILOC, because it is more powerful, it can return a series, it can return one value. It has to do more computation, slicing it, storing it, and returning it. And sometimes it is not efficient to keep calling ILOC, even though in theory it will work, it will not be fast. Then you need functions which only focuses on one thing, IAT, just pick one value. Did it answer your question, Nimisha?
Yes.
Yeah, and that you will see in many different languages, like in C++ as well. Like how you get the same thing, same job done, how you do it and which data structure you use it, it makes a lot of difference in speed mostly. But just to get the number, yeah, it's not a problem. But if you are using in a machine learning algorithm, then I would not use ILOC coordinate based. I use IAT.
Okay.
Yeah. So let us go for a new topic today. So Python 3, I'm going to create a new notebook. And what do we call it? Let us call it on and that's what it's going to be. So let's see what we can do today in, about other interesting things. I want to cover today Numpy. And that is another interesting aspect of one of the tools of machine learning that you should know. So, and you'll see what I'm going to do. I am going to, I've just put it on a node. Let's go through it. Cell type. Yeah. So now I wanted to show you this. So Numpy. So this is the Python data science ecosystem. What do you need to learn in machine learning mostly as far as Python is concerned? And this will get you most of it, like cover a lot of things. So pandas for tabular data, Numpy, which essentially sits in the middle, and this is for plotting. These are machine learning algorithms, libraries, all Python libraries. TensorFlow is also another by Google. Numpy is used by all of them. So it is inside at the bottom or in the middle of everything. It's the core. So it stands for, it means numerical Python. It is what you represent data with and do computation. And then all of the machine learning modules use it instead of plain arrays and matrices, plain arrays. So what would NumPy help you? Well, NumPy would help you manipulate data's vectors, matrices. So, and then we have been using it already. So you import it as NumPy. And then we also, NumPy is like more like a math-oriented representation. So it's essentially all the arrays are numbers or integers. That sort of data structure it's suitable for. Yeah. So okay. So that is great. So okay. So let's focus on NumPy. Let me share my. So there is. Yeah. So there is a question. Series is not a data type. It is a data. It is not a primitive data type, but it is a data type. You can say. It's more of a data structure. Yeah. But in the language of pandas, it's okay to call it a data type. Okay. So now I want to share the application. Great. Okay. So we'll go step by step. So I have a set of kind of topics that I want to cover on NumPy, and I want to go through it and what I want to cover. Here is what I have for you. So I'm going to cover here arrays, arrays indexing, data types in NumPy, and arrays math, broadcasting, matrices, and application to linear algebra. This is what I'm going to cover on today's lecture. Okay, great. Let me first make sure some arrangement on the too many windows I have open. Okay. Any questions so far? I'm going to on this. Okay. Sure. Great. So let me. Yeah. So arrange it a little bit more. Because this is a huge topic and it's an extremely important topic we should go through carefully. So what do I want to do here? So okay, these are the things we are going to do. So let's focus on arrays. So first of all, first things first, before you do NumPy, you have to do import NumPy as NP, as it says. So that we must do. So then how do I create a array? So here is one way we can do create an array. So NumPy is np array, and you can send in a primitive array of Python like this. This is what the primitive array from here to here, and it will convert it to a NumPy array. So what else can you do here? Array. So it's an array of length 3, shape say 3 comma. Okay, what is it of type? So NumPy multidimensional array. So it can have many dimensions. So this is what NumPy, these are some attributes. You can do a lot more interesting things than that. You can also access it like ordinary arrays. Okay, 1. Then you can print it also like ordinary arrays. they are printing in. You can have a two-dimensional array if you want to have. So for example, I can do two-dimensional array. How do you do? It's an array of arrays. So I'm going to have a, say, 2 by 3. That means 2 rows. In each row there are 3, values. So it's an array of arrays. So it's an array, and I need 2 arrays inside between them. So this first 2 corresponds to the first row and then second row. So first row, I want to have 3 elements, 1, 2, and 3, say. Second row, I want to have, say, 4, 5, 6. This is how I store it. And then the shape should be 2 by 3. First, let's print how it looks. Then print the shape. Shape is B shape. And then I want to access some element, access specific elements, one element at a time, say B 0, 0. What do you get? So first here it printed the array. So it's an array of array. This is how it looks. Shape is 2 by 3. 2 rows and 3 elements in each, or 3 columns. Or you can say it's a matrix, 2 by 3 matrix. That's what you would say in the proper language, mathematics language. And access one element at a time. Say I was accessing 0, 0, 0, 0. This is the one I was accessing. So this is what I could do with NumPy. Well, you might say, and what is the big deal about it? Well, you will see the power of NumPy when we do real calculations algebra. Say there are some useful functions here in NumPy I want to point out, and I want to show you how to use them. Sometimes you might need a matrix, 5 by 5 matrix full of zeros for some reason, just to initialize. So say this is a NumPy zeros 5 by 5. Oh, it did not print. Of course, I have to put a print statement. It's just a sign. What do you want to call it? Of 5 by 5 matrix of zeros. I would call it 5 by 5 matrix of zeros. Here you go. So you got 5 by 5 matrix of zeros. What if I wanted 1 instead of 1? So then you could do of ones. Then there is another function called ones. And these are very important. Sometimes you need an identity matrix. And we will see the identity matrix more in linear algebra when we do actual linear algebra. I think I shouldn't confuse these variables one on top of another. One, I should put it on different variables. And this is going to be C. This is, I want a full matrix of same value, 5 by 5, but of the same value. So this could, you could have achieved it like the above one by giving a value of full values. Full values. It's the same, one would be repeated everywhere. The same. Or you could, you can create these array of array structures. So then you can create diagonal matrix of all ones, which are identity matrix. It's like the one in normal, like in linear algebra, an identity matrix is a diagonal matrix with all ones. And this often works in the matrix multiplication that it has no effect. It doesn't change anything. It's like multiplying something by 1. So sometimes you want to create that. So the way you would do it is, suppose I want to create a diagonal matrix of 10 by 10 size. You use identity. I means identity matrix. Let's say 5. Matrix. So there you see the diagonal matrices are 1. Great. So you can also fill them up with random numbers. So how do we do random numbers? We know how to do random numbers. Numpy has a function. Any questions so far? Okay.
Kishori, what
Yes.
do you mean by values?
Say that again.
Full values. What do you mean by this full values?
Oh, full values is essentially the whole matrix is filled with the same value provided at the second argument to the function. Observe here 9. Everything is 9. It's a 5 by 5 matrix. Every element is 9, value of 9. Did it explain?
Yes. Okay.
Yeah, so that's how you can use. And we will see the use of these.
But in another case, it's taking a dot along with that. Why does it?
I see. Yes. So that is interesting. I want to make it, that is a matrix of probably integers. If I want it to be a float, then you get your dot. So Python has this habit of duck typing. Right? It automatically determines the value. If you usually put an integer number, it treats the value as an integer. Otherwise, it will treat it as a float if you have a decimal point. But now that you brought up a very good question, let's examine what type it is.
Yeah.
Where there is, let's remove this. So is matrix just a size? No. A matrix is, it has dimension and also you have to have a type. What type of values? Let's print it out. Type C. You'll see that this has NumPy array, and usually it will be associated with a data type. What type of data is it? And that is important, and often it is in a D types. Sometimes you will see it in print. You see, it's integer, 64-bit integer. Let's put a dot here. It's float. So did it explain your question? Yeah. So that's the idea. So it guesses it. So it's not only a matrix, it's a matrix of floats or integers. And because we did not specify there, if you really wanted to specify, another way would be, let's say integer 4. And sometimes some functions will have, not all, it will have a function like a choice like this, d type equal to, you would say int or float 64 or something. Depending on the program. Here it may not have that, but some of them, some have a type np, it will be np. And that you have to look up from the library to library. You see here, it's float, although I put 9 here because I forced it that treat these things like float. So that has to do with data type. And I can make it integer. NumPy has that ability to guess. So that's the idea about that. Okay, what if I want a bunch of random numbers?
Kishori, is D type only for matrices?
Yes, it's for matrices and series also, vectors. So any library like Panda or NumPy, they have this built-in D types so that you can control the type. But it can go with many types, not just matrices. Yeah.
Okay.
And also it's library dependent. So tomorrow if you come up with a library and you want to create your own form of calculations, this D type, now you might ask, why is D type there? Is it a part of the Python programming language? No, it is not. This is a convention and it has become so strong that people like to use it now. You can come up with some other way of calling it in your library, but it's not a part of the Python programming language. It's the module. But because of machine learning uses all of these techniques so much that these are becoming standards. Great. I have shown you at some point how to generate random number from NumPy. We just use it, but we never said that we want to this is NumPy. Today we are formally doing NumPy specifically. So NumPy is the NumPy module, and it has a module called random. Random is not just one kind of random. Randomness has many forms, and it could be random of numbers or random of integers, all kinds of things. So let's see here. One of them is random of, say, and you can suggest it. Essentially what it does, it generates a random number, usually uniformly, between 0 and 1, and that's where you are seeing 5 numbers. If I put 10, you'd have these numbers randomly, uniform. Of course, we could plot it with our matplotlib skills with a histogram, and you would see they are all uniform from a previous class. However, I might want a matrix. Why just a random number like this? In fact, NumPy can directly return you a matrix. So you just put the dimension. Oh, it did not like it. So because that likes the whole tuple, if it sees a tuple, then it will create a, there you go. So you have a random matrix. Each value is between a random number between 0 and 1, and it is of size 5 by 5. So let's call it E. Put it in a variable. Let's print it. A matrix of random values. So this is what we got. So that means you can create random numbers. So let's see what else next. So this way I have shown you how to create an array of values in NumPy. So let's call it arrays. Let's call it arrays. We have covered. Let's cell type is markdown. One, two, three, not too large a. So this is what our arrays we did. And we are supposed to do array indexing now. Let's learn how to do array indexing. Let's.
Sorry, I have one question.
Sure.
Like
Go ahead,
this random number is in this coding. We are not saying that it should be between 0 to 1 only. So how it's creating in
I see. So right. So in NumPy, in the module random, there are different distributions. The reason that, okay, let me go back to the screen. Actually, stop sharing, go back to the board. Right. Right. So, okay, so hopefully you note this down name, you have noted this name down, collab, it's very important. Random numbers, as you know, distributions, which we will cover again, have different types. 1, Sometimes some people want to generate a random between only 0 and 1 choices, 0, 1. And sometimes it's a normal distribution, minus infinity to infinity. Some are shaped like this. The numbers are more often in certain ranges. Maybe some are only on the positive sides. There are different kinds of distributions that comes out of different applications. They have different functions. But at the very root, usually, people start with a uniform random number between 0 and 1. From here, I can create other distributions by looking at the formula. Say, for example, if you want Gaussian, if I have a random number coming out of some random number generator, so here it is, say I have a the one I called is random, which is a uniform, it's called uniform between 0 and 1. So it spits out numbers between 0 and 1 uniformly. If you have a random number generator that can generate random uniform, by applying formula and computational techniques, you can create any distribution. That's why it is the most fundamental. But there are other functions which you do for others, like random normal. I think that's called array and n. So there are different names of standard. This one, random, it did not say uniform and all, because it's the one of the fundamental thing to do. That's why. So
that means that function, random function inside the NumPy will support 0 to between values between
yes.
0 to 1.
Yes.
Okay.
And I have noticed in most programming languages, when they mean random number, usually if you don't specify the plain vanilla one, like no options, always returns between 0 and 1. And from my knowledge, it's because the random uniform between 0 and 1 is the fundamental. For example, if somebody tells you, I want from a uniform random from 9 to 10, somehow, I need it. If you know a random number between that is coming from 0 and 1, what would you do? You'd essentially add 9 to it, right? So then it will always be uniform between 9 and 10. What if it is between 14 and, I don't know, 16, right? And all I get is random uniform here, uniform, right? Uniform between 0 and 1. Let's call it U instead of X. So how do I get this new random variable that is uniform between 14 and 16? Here is what you do. You know it's between 0 and 1. Great. What if I multiply it by 2? Okay, I'll multiply it by 2. So what am I going to get? It would get stretched out to 2, right? Because all the ones will be 2s. The ones that are closer to 0 will be 0, and it will be evenly spread out. I'm happy with this. But I need it over there. So if I add 14, so all the zeros will shift to 14, and the 2s will naturally go to 16. Same thing, it just gets shifted. I shouldn't draw it like this. I should draw 14 and 16 somewhere over here. So then you can say, oh, this X is equal to this. So essentially, you generate a random uniform, transform it, multiply it by 2 at 14, you get a new random distribution between uniform 14 and 16. So that's why this is very important. You can do all kinds of distributions from random uniform. Did it explain your question, Rupesh?
Yeah, yes. Sorry.
That's why it's very fundamental. Yeah. So let's go back to where we were. So
Kishori, I also have a question.
Sure, go ahead.
We had used np.random.random. So random is a module in NumPy.
Yes, that's a great question. Yes, absolutely. Yes, you are right. Go ahead.
And first random is the module name and the second random is the function name?
Yes. Yes,
okay.
Absolutely. So let's see how probably, I have not looked at the source code, but from our knowledge of Python, let's see how probably they might have written it. We briefly covered class, but I'm going to give you an idea. So probably they have a folder called NP somewhere they start with. And in that folder, probably they have this function, special function, an empty file called init.py. Any folder that has NP, or any folder that contains this file init.py, the special name to the underscores, init_py, it could be empty, they have nothing. It treats it like a library. So NP will be the first level. So you will have to do, say, import, you can directly import it in. NP, sure, from what? Random. Probably there is a file called random.py. And inside that file, probably has a function called random. And it returns a number, or it takes different values, tuples, things, depending on. And maybe there might be another function called random normal, RANDN. Yeah, so this is how probably they have organized. So you can also write classes like that. Did it explain your question, or do you have more doubts about it?
No, I got it. Yeah.
Okay.
Yeah.
So let us go to that. Great. So let's see if there is another function called rand. While we are in that topic, before we jump onto the other one, let's make sure np.random right. This normal distribution goes from negative to positive infinity. It can be any number, that means negative numbers and positive numbers. And say it's negative. So let's say I want 5 of them. Great, I got 5 of them. I want 5 by 5 of them. Oh no. So it does not support square, looks like. It only likes size, just one size, not like, but I will show you how to create 5 by 5 or out of. So maybe I can have 25. But this is not a 2D array, this is 1D array. But we wanted this. Well, randn chose not to implement this kind of a function. And I don't know why. Maybe it did. Let's try. No, it did not. Maybe it takes, you see, the same library, developers choose to write in different way. Here you go. This is the idea. So they don't need a tuple here. They need 2 different arguments here. This is where you have an array of array. So you see, they chose to implement in completely different ways. Here it takes a nice shape of the array, matrix, and here I had to fill it. But there is a yeah. So that's there. This is random normal, RANDN. If any questions, then we are going to go to array indexing now. Okay. So yes, you have created all these great arrays. So what is the use if you cannot access them? So let's create an array and see how we can index them. So first one I want to do is something called slicing. Let's call it slicing. And this is, you can slice any multi-dimensional array. Just like in Pandas we were doing LOC, NumPy also has something similar. So let's create a NumPy array, 2-dimensional array. right? So first, let's say 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10, 11, 12. Is there a NumPy array? Yeah, it seems like a NumPy array. Let's print it out. That seems like it. Could I have done this instead? Instead of an array, I could have also seen a range, right? Range 1 to 5. That Python function should also give me the same thing, because we know that these range functions 0 to, if you put just 6, it's going to give a, oh, it does not print. It's a, oh, it did not print it, by the way. What happened to this? There it showed up and it's not. This is something interesting I want to tell you. You'll see, now it is. So range gives you, here it worked great. Like it's here, range 1 to 5. This is something I want you to take a look at it. See, 1 to 5. That means, why did I have to put list around it? Why did it not work? It worked here fine. It did not work here without putting list. That's because range lists out a lot of numbers. It's essentially, you can think of it like a for loop, right? It is a lazy evaluation. And as far as I know, range is one of them. Some functions like this, Python does not evaluate. It knows that I want to do range from 1 to 6. Until you use it, like here or somewhere, iterate it, it does not evaluate itself. It's just lazy. Here, I'm going to show you. The first time I saw it, I was confused. You see? It is there, but it does not evaluate until you use it. Any question on it? This is a specific property of range. Yes, I have deviated a little, but I just wanted to let you know about some quirky thing about Python. And this is also, I could have typed it instead of doing all of these. 9 to 12, I could have done range 9 to 13. That would have taken care of it. I didn't have to type all of it, just to make sure you know. So this is an NumPy array I have created, and I want to access now different rows. Row, say R1, I'm going to access it as A. You have to put both, right? Comma, everything. First row 2, but everything. Row 2 because it starts, 0 is for first, 1 is for the second. So that's what that row is. So I can print it out for, but let's put another row. Row R2 equal to A1 colon 2. So it will be only 1, because 1 colon 2 means 1, and then it should be less than 2. So it's just 1. It's the same thing here. Then I am going to print it now. Print row R1 and then print R2. Row 2 is not defined. I probably did not execute this. Yeah, so I did not execute. So it prints row 1, row 2. So now, interesting thing, there is a difference. You see here, I exactly was able to get 1 row and I got an array. Here, I have the intention of getting a matrix, right? Because I'm putting an array here. It's like, I'm interested in several arrays. If you have several rows and several columns, what is it? It's an array of array, 2-dimensional. So it would be similar in that case, you'll see. See, it's the same. If you put exactly 1 element, it knows that no, he doesn't care about the being one array of 1 by 1. He cares about exactly one array, one dimensional. And that's where you do not see that. But here, 1 colon 1 is essentially 1 colon 2 is essentially like, 1. Similarly, if you say 1 colon, when you put colon operator, that's what it becomes. It's like 2, right? Let's try that. I put there. You got rows 1, 2, and 3. I mean, because of the indexing work. These two. So that's how you can access arrays. So just use this effectively. Otherwise, you'll be confused here. Why is it an array of array and here it's just one array? And we saw that in pandas too today, right? You can access like a series. If you do like 1, it becomes a series. And if you put square, because data frame is essentially like several series, it will put stack several of them together, so that it makes a lot of difference in this. So let's keep going with it. So let's talk about shapes and rows. In rows and shapes, how does it look? What does it mean? So let's say I want to print the row R1 and row R1 shape. So every of these NumPy object has a attribute called shape, dot shape, that you can access through. And it is supposed to give you what they mean. Let's again print the value and then row 2. Let's print out the shapes. This is what you get. First one, row, as we are accessing, is an array. So arrays are, this is the shape of an array. One value of the tuple and nothing. It's actually one value. It puts a comma. It has nothing. If you put 4 by 1, it would not be an array though. It would be 4 by 1 matrix. Because it's an array, it simply has after comma, there is nothing. Here it is 2 by 4. On the other hand, if I did this, you'd see, let's see this. You see here, it's 1 by 4, it has become. 1 row and 4. It's like a vector and matrix. Vector has only like one length. Yeah, just to make sure that you know the difference. So this is about the same. So what about columns? You can access column in a very similar manner as you did for arrays. Let's do column R1, except a colon. It's the first one, is the colon, everything opposite, and then you can see 1. Column, row 2 and 3, 2 and 3 say. I just call it 2 and 3. Yeah, it is. The all columns and 2 to 4. 2 and 3 is actually 1 to 3. It would be. Do we have that many rows? Yes, we have that column. I don't know why this R is, oh yeah, so this row, all the rows essentially, this is essentially saying that column. C, but anyhow, these have no meaning here for us. I shouldn't kill myself over that. Okay, so what do we have here? Let's print them out and see. Print column 1 and column 1 shape. Let's see what we get. And print column 2, column 2. So here you go. So here is your original matrix. Column 1, which is being printed here in this print statement, it makes an array out of it. So it says I want all the rows and focus on column 2 column, means its indexing starts from 0. So second column. So that means here you should see second of each row, second value of each row, 2, 6, and 10. And because it's an array, it doesn't matter. Array is an array, 3, comma. That's how it writes. And because you accessed one element. This should be a different story if you put an array here instead. Then you have a 3 by 1 actually matrix. That's not what it means. It will be done same. The second one is an array. So it's a matrix. Matrix, you want all the rows, and you care about the, first, middle 2 columns, 2 and 3. So this is 0, 1, and 2. So 2, 6, 10 is important to you, and 3, 7, 11. So essentially, first row will be 2 and 3 here, because you take row by row and only pick those columns, 6, 7, 10, 11, and it's a 3 by 2 matrix. The whole matrix is because there are 3 rows and 2 columns, so it has become smaller. Yeah.
Hello.
Mm-hmm.
Yeah, I did not understand why 1 colon 3 denotes the first and second column.
Ah, I see. Okay. Let me.
So is the
Yeah.
3 exclusive? It means
Yes.
first
Yes.
to
Yes.
third.
Yes.
Okay.
All of them. Yes. Absolutely. That's a good question. So, in Python, when you do any kind of operations that has a colon, say 5 colon 10, say, it always means start with this 5, 6, 7, 8, 9. It's exclusive. Always the right hand side of the column is always excluded.
Okay.
Yeah. Okay, great. So let's see. Okay. Cool. So that is where. So that's an indexing. So, but that is called slicing. Why is it called slicing? Because you have sliced through by putting one number or an array. You have subsetted it. What if I want to, actually I need to make sure I need to use the whiteboard a little bit longer now. I have something important. Yeah, somebody was going to ask a question. Go ahead.
Surely the attribute for shape is actually stands for row and column, row comma column.
Yes, number of rows and number of columns. Yes.
So that there it's showing as 3, 0, which should be 3 rows and 0 column. But actually the output is actually having 3 columns in 1 row.
Yes. So let us look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is our array of arrays, first row, second row, third row. So let's see here. So then what we did is, this is our A. Column 1, we say I want A, colon, comma, 1, colon, 3. When you put only colon, it means everything. For the rows, we have everything. We are going to pick all the rows. So this gives us that. 1 and 3. So this tells I should be focusing on columns 1 and 2 because 3 is excluded. So 1 and 2, this is the column 0, 1, 2, 3. These are the columns. Rows are numbered like this 0, 1, 2. So all rows, great, all rows 1 and 2, 1 and 2. So this middle section, where is my red pen? This is giving you the 1 and 2 or 1, and this colon is giving you the whole thing. Colon, it's coming from. So now look at it. The shape should be of this call object. Shape has two values, right? 0 and 1 value. The first one should tell you number of rows. Second value should tell you columns. Look at the number of rows. 1, 2, 3. 3. Number of columns. 1, 2. This is where our values are, right? So shape would be 3 by 2. So that's where it is showing here. So here is where you see the 3 by 2. Did it clarify your doubt, Rupesh? Or,
yeah, that's fine.
Kamal, yeah. So that's the idea. So shape gives you the dimension of the matrix, number of rows and number of columns. And this is now why do we call it slicing? I was about to tell you something about array indexing. I was already talking about indexing. What is so big deal about this? The big deal about it is this is a slicing because I slice it this way, slice it that way, one by one, one section, chop, 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 but what about maybe I want to pick this and this. I don't care about everything, right? So maybe I'm only interested in creating something like this and this, so that it looks like 2, 3, 10, 11. So that in that case, what I would love to do is that tell exactly, or maybe I want even crazier things, even strange things. I want this, an array of numbers. I pick this, then this, and this. And I want an array like this. 1, 7, 12. That you cannot achieve with this, right? With simple, straightforward slicing with 2 indexes. And now let's see how we can do that. So one way is this. Let's look at how I would like to pick A. So why can't I do this? Somehow I give A that, hey, you know what? I will give you a.
Ishwari, can you please share the board instead of the screen?
Oh, I'm sorry.
Okay.
Yeah. Yeah. Okay. Sorry, I'm going to place it again. Okay. Suppose I want to access in a very complicated way 2 and 3, 10, 11, these 2 blue ones, and create a matrix like that. I cannot do by slicing. Slicing only does cutting slices like this. These things. From here to 1 through 2 here, from here to here. But this I want to pick subsets. Or maybe I can do even strange things. This 1, this 7, and this 12. Right? 1, 7, 12. How do I do that? I don't know. I would like to have like this, these locations. One way you can think of is like, why don't you give me an array of coordinates? Like this is, I know 0, 0. This I know 1, 2, right? So let's see. This is 0, 0. 7 would be 1, 2. 12 would be like 2 and 3. Maybe you can give me 2 arrays somehow, like the first guy of each, 0, 1, and 2, great. The other one you can give me in another array maybe, 0, 2, and 3 maybe. And then I'll say, oh, you want the first guy, right? Then I'm going to look at this pair, one pair at a time. So this will give me, this pair will give me 0, 0. This will give me 1, 2. This will give me 2, 3. I might be able to do that. At least it gives me more flexibility. So that is called, that brings us to call array indexing or slicing by array indexing. Slicing by array index, or so let's go there and see. Oh, please do not hesitate to remind me if I miss something or ask questions anytime, and or even if I forget to switch my screen. It's very important that we all can focus on the material. Okay, so this brings us to the topic of, it's called integer array indexing. Let's write it down. It's called this is what we are going to do now. So now let's focus on an example now. Suppose I have an array. Let's create an array. So now we know how to create NumPy array, right? NP array and put in between all the data. So I want to create a 2-dimensional array. 3 by 2, 3 rows and 2 columns each. Right? 2 columns. Five, 6. Int A. Great. Something went wrong and I forgot a parenthesis. Invalid syntax. Something is invalid, it says. So that means I was putting NumPy array 5, 6. This is good. This is an additional one. Okay. So here is what you have now. NumPy array. Sometimes if I print like this in Jupyter Notebook, sometimes it prints nicer, but depends on the data structure, I guess. Okay. So I have this. So what I would like to pick is a few funny things. Like first I would like to pick this 1. Then I would like to pick this maybe 4. Then I would like to pick this 5. 1, 4, 5. 1, 4, 5. This is how I'm going to do it. Watch this. Print A, something I have to give. Of course, I know it has 2 sections, so I separate it by comma. And I'm going to put 2 complete arrays inside it. First one is 1 is 1, 1, right? 1. The one is 0, 0, so I put 1 here, 1 over there. The second one is 1, 1, that's 4. So 1, 4, 5 I want. That's 1. The other Y code row goes there. Then I want 5. 5 is the row 2 and column 0. So here you go, 1, 4, 5. So that is the beauty of not using those slices. This is how you can index it with this kind of arrays. Up here, we were using slices. Any questions about it? This gives you a much more sophisticated way of, or you can say this, essentially what it does is this. It's like an array as if we have created out of A 0 0, A 1 1, and A 2 0. It's like I gave you an array like this. So I handpicked one by one. So that's the idea. So this is called integer array. And in fact, you can even use it to change an entire vector. You can, say you want to add. So what you could do is that you can change one element from, say I want to create, let me give you an example where you can use it. It's a more funnier example. So NP array, range from 1 to, it's an array of array I want. So let's say 4 rows. Instead of typing, I think I should not. I create this range 1 to 4, 1 to 5, range 5 through 8, range 9 through 12, and range 13 through 16. One less as. Okay, so this is my array. Let me print it out for you. Again, the same problem. You see, it does lazy evaluation and it did not do anything. So I will force it to evaluate. Let's use its underscore and assign it to another variable so that it forces it to b equal to a. No, a equal to underscore a. So it forces it to evaluate. Oh, it did not actually. It remained lazy. How do we do that? Maybe we should multiply it by 1. But that is not possible either. I'll have to do, I don't have a choice, but I have to do a list around it. I'll do for 1, maybe the other guys will all be forced to change if 1 is changing. Okay, so it list. A list is also, it could be sometimes, if you don't use it, lazy. This is something I want to show you, these quirks of the Python programming language. There are certain things that will come through repeated use. Yeah, so this is the list. So you get the point. It's essentially a list. Its first row has 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14, 15. Oh, maybe that is a problem actually. It's not an array properly. 12 through, oh, maybe this is the error. That was the error. So it was not equal. One row was longer. So it was not able to create an array. Let me first make sure I remove it. Yeah, I think it should work because I'm making a NumPy array. Yes. So even if I remove list, NumPy should force it to spit out all the arrays. Let's make sure that we understand. Because NumPy array is a kind of a constructor. Here, same. And let me remove this. And I doubt that NumPy array can stop it from changing. Okay, great. NumPy array forced it to do. the transformation, the lazy evaluation. Okay, so we have this. Now, I want to have another array, call it B, and I want to add it row wise, say. Print B. Okay. So here is what I am trying to achieve. I am going to show in the screen. I have this list of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have another set of numbers, say, I don't know, 5, 1, 2, 3, 4. I would like to add this row, this into this row. So add this in this way. This is something that I want to do, say. So this will become, say, double of everything, 2, 4, 6, I don't know, 8. Then I would want to add this and this element wise, this element, and create this. So this would be, I don't know, this would be 6, 8, 10, 12, and so on. So to each, I take this slice and add it element wise. Again, take this slice element wise and create a new. So I want to do this kind of operation. I will show you how you can do it here. Right. So here, in order to do that, you have to do a, an operation. Let me show you here. So what you do here is that take the first array A and NP arrange. So 1, 2, 3, 4. So what does NP arrange gives you? NP arrange is also like range. A array. Say array of range. 4, say, what do you get? Essentially, you get the NumPy array. That's all. If you do this, actually, I should use NumPy range because probably it's not lazy evaluation, you see. So this, what I'm going to do, I'm going to say A dot A range is 4. I'm taking a vector A. For each of them, B, I want to add to each of them, you can do plus equal to 1000. So what I'm doing is that to each A, to each row, I'm adding the value 100. Let's see, what do I get here? Oh, range, NP range. Okay, so now I want to show you the value. So what it has done is that it has taken 100 and it kept on adding to each of them, each of these rows, and it added 100. So this is how you can access this as well. So this is an array, and then you are adding 100 to each for, with the B vector, B values, 1, 2, 3, 4, like this. Let's see. So maybe that's not the perfect example, but there are other forms of indexing you can do called Boolean indexing. So what I think is that maybe if you have any question, I'm going to explain this in more detail and we have to cover more stuff. Data types we will go to, array math we will do, then we will do how to solve factor, cross product, dot product and all. Why don't we take a 10-minute break here? But before we take a break, if you have any question, ask me any questions you have.
Yeah, one question I have.
Sure.
Yeah, like for NumPy only the array manipulation we can do, or any other thing also we can do?
You will do array and matrix manipulation. So
Only
today,
two things.
yeah, matrix manipulation. Today I'm going to show you how to solve linear equations of many variables. Like, remember from your 10th grade, you have these 2x plus 3y equal to 7, 4x plus 8y equal to 9. You have to solve for x and y. This kind of equation. Let's call it x1, y1 because x1, x2, it's easier. Symbols are. This equation to solve, suppose. Now in NumPy, you can represent this as follows. So you can essentially think of this as 2, 3 matrix, 4, 8, x1, x2. And you can write 7 and 9 like this. 7 and 9 like this, right? So the way it works is that think of them this and multiply together, bring this together, rotate it so that it looks like 2, 3, multiply, add them, 2x, 1, add them, multiply them, and then add them and equate to the first guy, 7. For the second one, this same thing, align it, then it becomes 4, 8, multiply them, 4x1, 8x2, add them, and equal to 9, lower one. So this is, how you do matrix multiplication. So what I'm going to show you is that these kind of equations can be represented in this matrix form, right? And solve. We are going to do not only for 2 variables, I'm going to show you, I'm going to generate 100 random numbers on each row. So 100 by 100, 10,000 numbers here, and there will be 100 variables, and there will be 100 some other numbers, and I'll show you how to solve x1, x2, all of them with this library, NumPy. So then, any other question? You'll see the great use of these things here. So let's then take a break for 10 minutes, and then we'll reconvene after this break. Okay, so now let's focus back on our NumPy. But before we do NumPy, we have to brush up some background on matrix or linear algebra. If you have any question, ask me and stop me, and ask as many questions as you want. And this part is important. As I mentioned, that even though you had to solve a set of equations, and in high school, we used to eliminate variable by variable, one by one. So you do something like, say, you'd express x1 in terms of the x2, and then substitute here. So you do something like 7 minus 3x2 divided by 2 and then you'd go ahead and substitute that here. 4 times 7 minus 3x2 plus 8x2 equal to 9. Use a different color. Yeah, 9. So then you would solve it for x2. And then you'd substitute the value and get the x1. But these kind of calculations you can do a lot faster if you do it algorithmically. One idea about that is that you can write it in this concise form with matrices. So now how do you write in this form? So let's see this. And that's why we need to visit some linear algebra, basics of linear algebra. And this would be a quick informal introduction to it. So first we want to talk about a vector. A vector we are used to in 2 and 3 dimensional. In 2 dimensional, we imagine it is like x and y, and then we have a point here. And we call this x component, and this is the y component. And we are used to writing it in x and y. Or this direction, we can write it as j, ij. So sometimes we used to write xi, yj. This is what we used to do in 10 plus 2. Maybe I should make my writing a little bit bigger, but now instead of x and y, you might have a third x, y, z. In that case, y, j, you used to have k, 3-dimensional. Instead of all these vectors in different directions, in x, y, z directions, people write like this form. And in machine learning, we are going to deal with vectors. It's going to be more than 3-dimensional. In fact, sometimes 1,000-dimensional. So the way you write here, you could have written in form x1, x2 to mean y, x3 mean to z. When you have thousands or hundreds, you can write like this. Say 100. And each one, in our case, most of the time is an integer or a number. Sometimes for numeric numbers. So this could be, say, for example, 2, 3.6, 4.7, goes on, and 7.8. Okay. So that's a vector. So what can you do with vector? Normally, in machine learning, when you talk about a vector of, you call it n-dimensional. Vector means n is some number. It could be 5, 3, 2. Example could be 2-dimensional, 3-dimensional, 100-dimensional vectors. You use this symbol. You make it a little bit bold. And some people use this symbol, or some people do this symbol, a kind of wave underneath the symbol. Or some people use bold. I like to do bold, bold, but lowercase x. So bold, 1, 2, some n. So then if they have another vector of the same dimension means n, right? You write like this, and z, and so on. Hey Neil, are you there in the class? I don't know. Yeah, hopefully he's with us. But if you have, do you have any question in the meantime? Just to check. Hey Rupesh, can you hear my voice?
Hey, this is Shivam. I can hear you.
Okay, great. Just wanted to check. Yeah. So now you will need these vectors for describing a feature, image, or height, weight, kind of blood pressure kind of numbers. When you have vectors, we can add it. X plus y is same symbol, except you do component-wise addition. X1, Y1, X2, Y2, X100 or Xn plus Yn you can do. For example, let's take two vectors that we will use as examples just to explain. X should be 2, 4, 5, 7. Y is a 3, 9, 2. So here in this case, X plus Y would be component wise add. 2 plus 3, so that would be 5, 14, 5 plus 9, 7 plus 2 is 9. That's how you add it. Sometimes you also call multiply it, combine it, multiply with a number. Say 2 times X means you multiply each element of X vector with 2. So that would result in another vector. Addition of two vectors also give you a new vector. Right? You can use a symbol equivalent just to say Z. I can call it Z. This 3 parallel means equivalent. If you do 2 vector, that would be a new vector that you multiply each element by 2. So in this case, 4, X is this, 2 times 5 is 10, 2 times 7 is 14. I can also add this to Y, 2X after that plus Y. In that case, 4 plus Y, 7, and it's 10 plus 9, 19, 14 plus 2, 16. So this is how you can add vectors. So when you multiply a number with a vector, you multiply that number component wise. And when you add two vectors, you add component wise and create the new vector. So then you could also have this plus Y, even divided by 0.5 maybe, 0.5 Y. What would that be? So that would be 2X is the 7. Half of that Y is, I don't know, that's 1.5. So that makes it 8.5. So this is the, yeah. So then, oh no, this is a mistake. I should have picked up from here. 4 plus half, 1.5. That is 5.5. 10 plus half of 9, 14.5. X is 14 plus half of 2, 15. So you can do this. Now, anywhere you have, often you will see instead of this 2.5, they will write like this. A is some number. B. And it will be essentially what, because it's done component wise, AX1 plus BY1, comma, AX2 plus BY2. This should be the resulting thing. AXN plus BYN. This is all going on. This is called linear combination of two vectors. It's linear. There is no squaring going on here. No square root, just straight up. And multiplying it by scaling, that's okay. It's still linear and combined. It's called linear combination of two vectors. So it turns out that if you look at our two-dimensional vectors space, Cartesian coordinate, and say these are X, Y, J vectors, right? So let's take any two vectors here. Let's call I is, the way you represent vector is the coordinate you put here. So this is X coordinate is some, suppose amount 1, and this is say 1, right? So this is for visual representation, but vectors, you should think of them in an abstract way, but this visual will help you. Now let's look at these two vectors, how we represent them. And what is a vector? This is a point from 0 origin to that. So let's call it I vector. And let's call it J vector. This, the component, the X component for this guy is 1. And Y is 0, nothing going up in this side. This is the I vector. J vector is, on the other hand, nothing on the X because it's in the same place, go up Y, 0, 1. Now let's look at any vector. Somewhere, suppose this is, say, a vector of, say, 1.3 in the X direction and 1.1 in the X direction, Y direction. This is a new vector, my X vector. See, essentially, I can create that vector by combining them. All I need to do is that 1.3 I times 1.1 J. This 1.3 I can write as 1, 0 plus, or this is 1.1, 0, 1. What is this one? This one is 1.3, 0 plus 1. No, this is 0. First one is 1.1 times 0 is 0. 1.1 times 1 is 1.1. And then I am adding it. This is 0 plus 1.3, 0 plus. So that means what? I have linearly combined them to create this vector X. So give me any vector here. I can always find a combination of between I and J. Maybe I don't know. I will have to find out what A and B. I have to pick them appropriately, but I can always create your vector in this, if these are the X and I's I am picking. However, if both of my vectors are the same one exactly, J also I call I, there is no way I can have a Y component because they all have something like, okay, another thing here. Suppose I have another vector, this is IJ, I have another vector I prime, and this goes at 2. So that one is I prime 2, 0. Even then, I can create X. All I need to do is do this. Instead of 1.3, I need to divide it by 1.3 because there is already a 2 here. I primed plus 1.1 J. Here, instead of 1.3, I do divided by 1.3 here. Right? I think that becomes 0.65, 615 or something. Right. This, because there is I prime already has a 2 hidden here, so it will balance out. So even though the vectors are, if the vector is there and it's longer, you can scale it down by linear combination. So you can produce any vector. But if the vectors both I and J are, there is no component on the Y side, both are on a line, then you cannot get anything X and Y. So that means if vectors are linearly independent, that's a property, that means they are not fully aligned, you can actually create any other vector out of these two vectors just by linear combination. And this is something we'll use a lot. Any question on this? We don't have to go too deep into it, but just to give you the jargon. And we are going to solve equations based on that. So now let's not worry about vectors. Let's worry about matrices. Okay. So vectors, there is another property I wanted to say. If we have vector X, you can do a dot product. And that product is essentially component-wise multiplication of the elements. So it's like X1 and sum them up though, after. So x1 multiply and add them up, right? So here 2 times 3 is 6, 6 plus 5, 45. So this is 6 plus 20, 65. So that would be the dot product. So that's what you do. Dot. So now I want to quickly go to matrix and matrix multiplication. And that's what we would need for solving our linear equations. So a matrix is more of a rectangular shape. And it has a dimension. So it's say 2 by 3. The first one always talks about the number of rows. Usually, a lot of people would use the symbol n. And the number of columns, m. Or n cross m. N could be any 2, 3, 4, any number. Now, in this case, two rows. So we'll have 2 rows and 3 numbers. Anything, 4, 6, 5, or 4, 5, 6, 8, and 9, 10, 12. This is a 2 by 3 matrix in 3 columns. This is a 3 by 4 matrix. 4. That is a 3 by 4 matrix. Or together they are called the dimension of the matrix. What is the dimension of this matrix? 3 by 4. 3 rows and 4 columns. That is something we will need. So now what can you do with matrices? Well, you can add them. So we might need this. We don't need this. We have gotten the vector. So let's use. And matrix could be of any dimension. So for example, a JPEG image or a black and white image could be many numbers, have different pixels. The whole screen you can think of as like pixels. So it's a 750 by, I don't know, 360 image would be these many rows, 360 columns. So it's a matrix. Each one is a value between 0 to 255 for brightness. That's an image. And we will do some image related load into Numpy and show you. That's one suitable. And that's why Numpy is useful, because every element is similar value, homogeneous value. They're all numbers. They're not like one string, one number. They are suitable for algebra, linear algebra. Next, matrix addition. If 2 matrices, let's call it a 2 matrices. Matrices are usually denoted by this symbol capital. Usually vectors have this lowercase symbol like X, Y bold. Matrices have either this, but they use capital bold. 2, 1, 4, 7. This is 1. Another bold. 8, 6, 3, 2. Matrices can also be, they have that formula for linear combination. So something like 2a. First they can be added, 2a. So you multiply each element by 2 here. It becomes 4, 2, 4, 8, 14, 6. So then you can say, you can multiply b also by something or not. 3, say 12, 24, 9. Then you can add them or even subtract them, 3b. This should be 2a minus 3b, 2a minus 3b, it's minus 8. Oh, It's all going to be negative numbers probably. Anyhow, we'll do that anyway. Minus 22, minus 14, minus 19. This is 14 minus 9, 5, then 6, that's 0. You can write like this. This is matrix addition, so you can also write like. So now here I want to talk about matrix multiplication. That is important here. Matrix multiplication. This is interesting. So you have two matrices and you want to multiply. This is called, by the way, dot product of vectors. Dot product of vectors. Now, matrix multiplication is somewhat different. Some of you might already know. So you can multiply two matrices, A times C, just give a name. There has to be one interesting property. And I'll tell you why it is required. So let's rewrite A here, 2, 1, 2, 4, 7, 3. And here I have a 1, 2, 1 matrix. What I'm going to do, the way I do this multiplication is take this slice, multiply it element wise, add them up, and place the value here. Do the same thing with this now. Let me switch this. This one again, do the same thing. So take one row, do the dot product with this, and then put the value here. So here is an example. For this, what do I get? This and this rotated. So think of it like this slice 2 times 1, 2 times 1 times 2, add them, 2 plus add them, 2 times 1. That's for the first row. First row, and again with this, 4 times 1, 4 times 1 plus 7 times 2, 3 times 1. So essentially, consider this row and forget about this row. Multiply, tilt it like this, multiply element wise, pair wise for each. First of the other one, second with the element of the other one. Add them up. Whatever number is, put it here, and then do the same thing with the other row and forget about this for now. So this, after doing this calculation, 2 plus 2 plus 2, 6. 4 plus 14, that's 18 plus 3, 21. Look at the dimension of the matrices here. Now, this is a 2 by 3 matrices, and this is a 3 by 1 matrix. And this is a 2 by 1 matrix. So that's the idea. If it is M by N matrix, it could be any number, or N by M, and if this is of M by K, whatever it is, in our example, this is 2 by 3, this vector is 3 by 1, then ignore these two. It becomes a matrix of 2 by 1. Just ignore the middle two. Or in other words, N by K. So that means when you want to do matrix multiplication, you have to make sure the first guy row dimension, column dimension should be the same as the row dimension of the second guy. As a result, you may not be able to do this. For example, here, C, if I flip it, C is this. 3 by 1 is 2 by 3. This do not match. So you cannot multiply. So that means they are not compatible. So this is a rule about matrix multiplication. So that's how you have to see, are they compatible for multiplication? Then you can define this. Any questions on this?
Kishori, what is the significance of multiplication of matrix or the
Right.
dot product of vectors?
Right.
So why do we have to do this?
Yeah, I see your point. Yeah.
Yeah.
So that is a good question. I will give a real life example here. And I will give you another example why we need this. Think about X value vector tells me about the price of something, price of a computer, say, or something, or say grocery, something. Say, I should give a very simple example, say book, price of per book, something. One, this is per pencil, $2. Then per 2 rupees. Then say I have per price erasers, 3. So book, pen, and eraser. So they are of different price, although the prices are a little bit funny. So maybe make eraser 1, make book 3, pen is 2, eraser is 1. So I have another vector. I got 4 books, 3 pens, and 2 erasers. So what is the total value? Total value is simply the dot product of this. 3 books, per book price is 12, plus what I got 3 pens, each pen cost me 2 rupees, 6, plus 2 erasers, 1, 2, so that makes it 820. So 20 is the number here, so total value. So it is for essentially component-wise calculation to aggregate. Another one is this dot product. It's more of a physical example. If you have 2 vectors and you write out the components and you do the vectors, let's call this vector A, which has x1. From now, we will not call this y, we'll call it x2. It's x2. So the value is x1, x2. Another value is x1 prime, the values. These are the coordinates. These are the actual values. So I want to know, if I draw a perpendicular, how much similar they are. The more similar they are, the bigger will be the dot product. A dot B, or I should use bold, right? I will not put this dot, it means multiplication. There is no need of parentheses here, it's a number. It's just a number, right? So essentially, this number tells you how much together they are on the same side. For example, if you took the dot, let's consider 3 scenarios. I have 2 vectors, A and B. In this case, say the vectors are of unit length, A and B, the dot product would be closer to 1. If 1 is here, 1 is there, A is A and B, A dot B would be closer to 0. And if A is facing this way, B is facing that way, A dot B is be closer to -1, negative. So dot product gives you an indication of how similar one vector is to another. When it is 0, they have nothing to do with each other. You see, they are perpendicular, like x and y, because one change of one x has nothing to do with change of y. It's in a completely different direction. And if the both of the vectors are facing the same way, their dot product would be larger. And if they are of unit vectors, they will all be between -1 and 1. So this is used to measure similarity. And I will give you an example later about when they do document classification. Say you have a set of books, text, and somebody told you that use a machine learning algorithm and classify the books into romantic, action, and adventure. So then what you do, you take all the words in the book, create vectors, and create dot products. The ones with higher dot products, they are similar items. And that's used in machine learning a lot. And that's one of the uses of, say, dot product. Kashyap, did it answer that question at least partially?
Yeah.
Yeah, okay.
And also when we say vectors, so it doesn't mean that it should start at origin, right?
Yes, it does not have to start at origin. Only when you use coordinate representation, then only you think of origin. It's a representation. Vector, you should think of something that has a direction and some orientation. Yeah.
Okay. Okay.
And to us, it's even more difficult thing. To us, it's very abstract. It's a set of an array of numbers that have the same dimension, and they have some rules we can operate on them. And those rules are out of convenience, made by mathematicians, but it's not like it is coming from nature. Somebody is giving up. These are mathematicians' construct, but that are useful in solving problems. At least, yeah, that's how we look at it as. So now I gave you the example of a matrix multiplication. Now you might ask, what is the use of this? How do I use it? Here is an example I'm going to show you how to use it. Oh, I did not give you the, yeah, you were asked me, what is the use of a matrix multiplication? And here is an example I'm going to give you. Say you have a set of equations, x1, 2, plus 3, 4, 7, x4 is 19, 2, 3, x1, 4, x3, 12, x4, 1, x1 plus 3, x2 plus 7, x3 plus 8, x4, 10, 2, x1, x2 plus 6, x3 plus 9, 12, x4 plus 7. Okay, so this I did not write, it means it's 0. So look at these equations. It is a large set of equations, and I would like to design methods that can solve these equations. But before that, I can write them in this form, this whole equation. So what I do, I look at 2, 3, 4, 7, 2, 3, 4, 7, 3, because there is nothing, take it as 0. It's like thinking 0 times 2. That's why I didn't write it. 3, 0, 4, 12. Then here, think it has a 1 multiplying. 1, 3, 7, 8. Then 2, 18, 6, 12, 7. 2, 18, 6, 2, 18, 6, 12, 6 12. Okay, 7 is not there. Now I write x1, x2, x3, x4. That's a vector or another 4 by 1 matrix. And then I write like these guys. 19, 7, 19, 7. So think about it. When you do this multiplication to get the matrix, you are essentially going to multiply this, and put it there. So you could essentially represent this as 19, 7, 19, 7, suppose. So I don't know why there's a repeated pattern. I forgot I was generating. So essentially this, you can say, this multiplied by this, what happens? 2x1 plus 3, x2 plus 4, x3 plus 7, x4. Think about this and look at this. It's the same one. This will also be very similar. 3, x1, this 0 multiplied, doesn't matter. 3, 4, x3, 12, x4, and so on. So you see, you could take a system of linear equations and represent in the matrix format. And now once you have this format, a lot of properties of linear algebra and algorithms can be exploited to quickly solve such equations. And that's what we are going to do. So any questions so far? After this, we are going to actually show how to solve these equations. Okay, so let us go to the computer and see how we can solve them. And I'm skipping a little ahead, but we'll come back to some of the topics later. Let me see. Okay, great. So you should see my screen, and then let me actually minimize the. Okay. Nice. Okay. So what I am going to do is that, let's see if we can directly show you how to solve equations. Okay. So let's first do some array arithmetics. Array math. So let's look at, I type this out, and just let's use one of the arrays we have used previously. So here I have defined two numpy arrays, x and y. It's of rows. The first one is of shape, which we'll find out, and both are of type float. You see, I'm explaining. Let's look at their dimensions. Shape will give the dimension. So first let's print x and then print x. What does it tell us? This is the matrix. We know that. First row, second row. Of course, this is the dimension. 2 rows and 4 columns. And that links us to our matrix dimension. Now let's look at y. Y matrix, y. And then y dot shape, that attribute. So x goes up y, and y has 4 columns and 2 rows here. And same, I should put here a new line. Make it cleaner, yeah. Maybe 2 new lines, okay. Okay, so that's what I mean. So this is your shape, this is the shape. Both are of the same dimension. You can add matrices like I did only if the dimensions match up. Right? So let's first print X, our X. This is your X. This is your Y. I'm going to add them, X plus Y. X plus Y, print X plus Y. They can add like ordinary numbers. So Numpy matrices or arrays, they have added it component wise. 1 plus 5 is 6 here. 2, it's a first row second value of here X. Again, first row second value of Y. If you add them, 2 plus 6 is 8. So you are doing matrix addition here. You could do matrix subtraction also. It's the same. And X minus lowercase x minus Y. X minus Y. So you are able to subtract it. X minus Y. X is 1 minus Y. So that's 1 minus 5 is minus 4. Same thing with this. Let's look at the 13. What's about 13? So X is 5. Y is minus 8 already. 5 minus 8 is 5 plus 8, 13. Now, not only that, you could do something interesting. X is not a, what is X now? Print type X Y. So they are Numpy two-dimensional array. ND array means N can be anything, 1, 2, 3 dimension like that. So that means there is an interesting thing to notice. These are element-wise product, or element-wise division. You can do even element-wise multiplication. Let's do element-wise print. Element-wise product. You do print X times Y. So here what happened? 5 times 1, 1 times 5, 5, 2 times 6, 12. Here. This is how you get the number. Here, for example, the last one, 5 times minus 8 is minus 40. But this is not matrix multiplication. Matrix multiplication has that strange rule I explained. And we have to get to that. But anyhow, so this is what I want to show you is that you can even apply element by element division as well. But you have to be careful with zeros division. There. This is infinity. There is a 0 probably somewhere. Oh, here 0. INF means infinity. So this is the property of these. Now, if you want to have, now let's say I want to do a Numpy, say matrix multiplication or vector product, then there are separate functions to do that. First, I want to show you another stuff here. First, let's consider two vectors, dot product. First, let's V is equal to say Numpy array. I have two values, say 9 and 10. I have W, I have NumPy array 11 and 12, I have 2. So now I want to do a V times W. This is going to be element wise multiplication of these two arrays. So 9 times 11, 99, 10 times 12, 120. Great. But there is another type here I can show you. V dot W, V dot W. What does it do? According to our dot product definition. Look at the screen. Here, you take element by element, multiply, and add them. It's not a factor anymore. It's just a number. And this is the dot product you are going to see here. Yes. So there you are going to see print the dot product value. 219. How did I get 219? So that is because 9 times 11 plus this. So essentially 99 plus 120. So that's a dot product. So that's how you can calculate dot product of matrices and vectors. You can also do cross product, which you will get later. I wanted to show you something also. NumPy has the concept of matrices as well. And then broadcasting. Essentially, matrices are created. I want to show you one example here. Here we have our matrices X and Y. Right? Let's print X and Y again. Y, and also type X, type Y. So they are NumPy arrays. So I can create them matrix. Although NumPy multidimensional arrays look like matrices, when you multiply them, they do not form the matrix product. So for that, there is another NumPy thing here. You can call it NumPy matrix. So you can feed probably the NumPy, the X. It will become a, this time it will become a matrix, see? And there are some advantages. I will tell you in a second now. NumPy matrix. And I'm going to type print A, B, type A, type B. So matrix. So matrices in NumPy are like mathematical matrices I just showed you. You see, it looks same. It has the same rows, but they are different objects. They are matrix objects. So what is the difference then? It looks similar, but doesn't mean that they behave the same way. Let's look at this example. Print X dot Y, that is the element-wise product. You get that. In matrix, you will get matrix, or print Y dot X. It's the same thing. Right? Now let's look at matrix multiplication. Are they compatible? Let's make sure. Let's look at their shape. I want to do this, A times B. So I want to make sure their shapes are there. What is their shape? A dot shape, B dot shape. Remember, the row number of columns in the first one should be equal to the number of rows in order for us to be able to do that multiplication. Does it match? Not really. I can do B by A. Probably I can do B by A, B times A matrix. That might be possible. Oh no, I can't do that actually. 2 by 4, 2 by 4. We're in trouble here. So we need smaller number. We need smaller. These matrices are not suitable for matrix multiplication. We should take smaller xy. We will create smaller xy. Let's create smaller xy's because the dimensions are not compatible. Let's create from the beginning. Let's call it x and here. So then let's print. Oh no, let's make them the same dimension, equal both. Okay, so they are both 2 by 2 matrices. And let's now print x times y. So you get element wise. 1 times 1, 5, 2 times 6, 12, and so on. Now let's create vector out of them, matrices out of these ND arrays. They are matrices. They look similar. The values are 3, 4, 2, 2, 3, 4, 2, 2. X and y values are 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So also let's print the shape. Right. Shapes are also 2 by 2. Great. So then now think about this print x star y. I'm going to do, and note that A is I transformed into matrix object out of that array. B also I did from y. It's the same thing by looks, but look at when I do the multiplication. The values are not the same. This is matrix multiplication, and that's why I converted into matrix, so that I can get these linear algebra methods for free. And this is going to help me to solve equations, algorithms that solve lots of equations, applications to algebra. For example, let me give you an example right now, how to solve it. And that's where we'll stop at. Do you guys have any question? I'm going to solve one equation, and with that we'll end for today's class. Let me take a matrix, 100 by 100 matrix. Let's call it A, NP, NP, random. So let me first explain what I'm trying to do on the board. So I am going to take a matrix, system of equations, where there are 100 variables each. So it will go on like some number, say, let's call it A1, X1, A2 is another number like 2, 3, these are A's for me. A1, A2, A3. Actually, I should call it A11, first rows 1, first rows 2nd. I should, first rows 3rd, first rows 4th, and so on, like this. A11, A12, X2, and so on. You see 100 of them, 100, or like X100, and some value, B1. Like this, I have 100 equations. So it's if I look at only the A's, and this equation can be exactly written as all the A's, A12 and so on, A100, A101, A102, and so on. And then the vector of X1, X2 up to X100, and a B vector, and I'm going to solve all the X's. I'll generate these numbers randomly, all these equations, because I don't have any specific problem. So I think somebody has a question. Okay, I see, okay. Oh, why 4 times 6 output is 14, minus 14, let's see. Ah, I see. 4 times 6. Great, I see. Okay, that's a good question. So that is because you have to follow now the rules of the matrix. Why? Let me come back to this. So 1, 2, 3, 4. This is my x is I initially had 1, 2, 3, 4. Y I had 5, 6, 5, 6, 0, minus 8. 5, 6, 0, minus 8. Now what I did, when I had this as a like a ND array I call it, NumPy array, ND array. When I do x times y, it is just this times this is 5. This times this is 0. 2 times 6 is 12. 4 times 8 is 32. Minus 8 is 32. Now I created matrix out of them A. From here I created a matrix and B matrix. Now when I want to do A times B, the rules have changed. This is how you do matrix multiplication. I showed you only one vector, but what if you had another vector? I'll show you that rule. So again, look at this 5, 6, no, 1, 2, 1, 2, 3, 4, 5, 6, 0, minus 8. Look, let's look at this. This is the matrix rule multiplication is going to happen. This, let me see, there is another question. Okay. Okay, great. So great. So what happens is that matrix multiplication, this multiply the first element wise and add them. 1 times 5, 5, 2 plus 0, 0, that's 5. This is coming from this and this. Let's look at the next one. This with the next one. Or you can do the next row also. It doesn't matter. You can do this again with this. 3 times 5, 15. 4 times 0. And that comes below this. 15. Now focus on the next column. This with this. 1 plus 6 plus 1 times 6, 6 plus 2 times 8, 16. So that's like 22. What about this? This again with this, the last one. 3 times 6, 18 minus 32. 18 minus 32. That's 14. Minus 14. That's minus 14. So that's how we get minus 14 there. That's the matrix multiplication rule. So this is pointwise. This is just a convenience of multiplying to the ND arrays. When you convert them into matrix type objects, the rules of actual mathematics of matrix multiplication kicks in those objects. So now let me create that matrix I showed you there. This is, then I'll have to create a B vector and I'll solve this equation. X, I don't have to say anything. It will imagine the system that, hey, I have a bunch of X and I'll solve it. So all I need to supply is this matrix 100 by 100 and a vector, that B final side of 100 numbers, and it will solve it. It will assume that there is a bunch of X. I need to solve it. All right. Let us create the random numbers. It's easier. We don't know what we want to solve now. We are not solving any image problems. Random normal. How many? 100 by 100. Do I get it? Let's see. I'll print it for you. Oh, too many numbers. See? Look at the shape of this. 100 by 100, large numbers. I create the B that on the right side. Random. I just need 100 by 1. This is also, yeah. Now I have, let's print out B. In B. Large number of numbers, you see, lot of numbers. Now I want to solve. Let's not print B, let's print their shape only. Great. So now I need to solve. What I want to do is this call. Let's solve A, X is in B. I'm going to solve it. Now this is how NumPy algorithm will solve it for you. NP, you provide linear ALG, another module that solves linear algebra, solves A and B. It has solved. In theory, really, let's see, print X. Those are your solutions. So now let's look at one thing. Can we reproduce the first equation? Those are the solutions. But now what I'm going to do is that take the first row, do the dot product with this, and it should give me the corresponding B. It's like this, if I know the value of X, the first one, this equation should be equal to what was on the other side, 19. Then we would know it's true, probably it's solving. Let's do that test. So now how do I grab the first row of A? Can I do this maybe? A, how do I do that? A, first one maybe, like this. Let's see. Yeah, looks like we can do that. A, oh, I need to share this. Oh yeah, I'm sharing the screen or not. Oh yeah, I'm sharing the screen, yeah. A, I want to check the first equation. First one should be exactly equal to the first value of B. Let's first print B before. Let's first print B. Print B values. I mean, I want to print the first value of B. How do I do that? So it's a, I can do, I think 1, 2, I can do 0, comma 0. So that's the first value of B. That's the B1 essentially. So after I take the x's and multiply A, so I should expect A colon A. How do I get the first row? 1, comma. This is how I get the first row. Now I can do dot product on it of the x. Did I get anything? No. It's not the first row, it's a 0. 0 means first always. See here, you got your solution. So let's print B101. Let's see. Oh no, sorry, 10 is the only one. Right. So that one. So that one should be here. This is the value you got. So let's print them side by side. A 0, comma, colon, code. This is, I'm not doing anything. I'm just making sure the solutions are correct. Yeah, the solutions are correct, you see, after I multiply this. So that's where we will we are going to stop, but let's take some questions now. You have seen a lot of things, how to even solve 100 variable equations.
Kishori, when we took np.linearalgebra.solve AB, but AB is not matrix, right? Here we took just random numbers.
We created matrices of random numbers.
Okay, so we need not take we were taking it before np.matrix we were using, right?
Yes. Here it could even take array, right? It could take array even.
Yeah,
So
here it's taking array directly.
Yes, it was taking as an array, but inside solve probably they transform it to matrix.
Matrix. Okay.
Yeah, inside.
So we did not feed matrix here.
Mm-hmm.
We can feed
I
array
see.
and
Yes. You can send them as array. I think if we convert it to matrix and send it, it will also solve the same thing. Because when you send something to the solve function will check, is it a ND array or matrix? If it is ND array, then it will convert it into matrix and then do the calculation in matrix.
Oh, okay.
Yeah. So Python always tries to do this intelligent thing that, hey, if maybe it's normal for people to think like this, so then they will try to adjust you for that. Like they will try to write the functions in a way that guesses and tries which one makes sense. Yeah. Any other question? So next week, there are 2 weeks, there will be no classes but homeworks. I will be traveling to Cambridge University for some data science research conference. But I will come and resume the classes after that. But in the meantime, I'll send you materials and send us emails for any material you are looking for, and try to make use of Colab. I'll also check your home assignments and give you information, feedback. So try Colab that I showed you today. If you are not able to install Jupyter, all of these things should work. Yeah. Any other question? Okay, so let's stop the class here for today. And yeah, we'll be picking up later.
Okay. Thank you.
You're welcome.
Thank you, Kushal.
Yeah, you're welcome.
Thank you, sir.
Yeah, welcome.
Okay, thanks, Kishori.
Yeah, you're welcome.